get this before we throw another thing at you. So make sure you're following along with me. Nothing to reduce. So we look at your denominator. There's your domain restriction. You only have to take this out once. So -3 is the value that you can't use. Take it out of your domain. Therefore, as your vertical asymptote, you can't use -3. And in your calculator, you'll see at -3 it says error. Here's your asymptote, -3. Find your horizontal asymptote. This is x squared. This is x squared. Make sure you find the highest exponent for your variable. So your highest exponent is 2. They're both the same. When the degree in the numerator is equal to the degree in the denominator, take the coefficients and make a ratio. Y equals A over B. It's okay, Brianna. So y is equal to 1. And you have no slant. The slant only happens when there's no horizontal and the numerator is 1 more than the denominator. So put that out there. Now, here's the problem. When we look at this graph, can we tell that it kind of jumped over? You might not be able to tell. What might help a little bit is you can visualize where your x is, and you can visualize this one riding along your y. This one looks a little bit higher, doesn't it? I mean, it's hard to tell. So maybe it would help do your window a little bit smaller. Do your window so you're just looking at that strip around the x-axis. You want to go from where your asymptote is. So maybe we want to make our y's go from -2 to +2. Let's just see what it looks like. Let's see if we get any closer to this. So can you see it better now? Here's your x equals 3. Here's your y equals 1. So see, this one's fine. The end behavior is going along. It's never going to touch that asymptote. This part of your graph, it actually jumped your horizontal, and what happens is this. It comes back down, and it uses that asymptote for its end behavior. That's what a horizontal asymptote is for, to monitor the end behavior. Kind of like the barriers on a road. You know, when they change lanes on you, you see the little signs that say change lanes, and they have those little barriers there. You don't cross the barriers, you stay within those barriers, right? So it kind of guides you along the road. So it's used as a guide, and it can cross a horizontal, never a vertical. So we see it come back, and if you want to see it a little bit better, expand your y, your x rather. Let's look at that -x a little bit more. Let's go to say like -30. Let's see if it looks a little bit tighter over here. Can you see it now? Can you see where it jumps? Here's your y equals 1. Do you see the jump? Do you see the maximum now? And how do you know? How do you know that it's doing that? You may not realize it. You may not realize it. But a good way to tell is your table. Here's your table. Let's take a look at your negatives. Y equals 1 is an asymptote, right? So I should see everything under 1. But look what happens. These guys are over 1. Wasn't y equals 1 your asymptote? Everybody should be riding alongside of that. But it's not. It went greater than 1. And as you look, it goes higher, but then look at that. It comes back down again. See it? See it increased from here to here, and then it decreased again. So it had a little blur, a little jump. So use your table, use your graph, use your windows. Look at the part in detail when you need to see what's happening. This is probably the hardest thing to get, because when we do a Zoom 6, it doesn't look any different. But you kind of can see one was a little flatter than the other. So one probably misbehaved. So he kind of jumped over the horizontal, but then it comes back down and uses that as its end behavior. Okay? So we have to find this maximum. So back to our graph, we can find this maximum point. That is a relative maximum. Because when it jumps over and then comes back down, it has to be some kind of high point to bring it back down again. So we find our maximum for this guy. If you didn't do it with me now. We're to the left, then we're going to the right. Oops. Go to the right and find your maximum. Okay, so it's like -6. It's close to -6. Your calculator does weird things. This is actually 4/3, but you could leave it 1.333, or you could leave it 4/3. You know your third is 0.3333. So if you want to flip it to a fraction, that's fine, but this is -6. So it's got a maximum point at -60. So we know this maximum point here is at -60. Oh, sorry, -6, what did I say? 4/3. Okay. Now, the rest of this should kind of fit into place. You need this point, that maximum, to also get your range. You found your domain, you know what you can't use, your asymptote was there, that was all good. Your relative max helps you find your range. Now, this one is only going to stop at 1. This one jumps over, it goes a little higher, goes right up to this one. So therefore, your range is going from -infinity to 4/3, or 1.333. You can keep the decimal, that's fine. The other one is -6. Your calculator just behaves a little differently. You also have now an increasing decreasing there, because you're increasing to get to this point. You've got an increasing to get to this point. Then you're decreasing from here to -3. You can't go past -3. Then you're increasing again from here to here. Okay? You're decreasing in that little bit from -6 to -3. Then you're increasing again. They don't have to look uniform. They look a little strange. Sometimes you see a little loop on top, a little loop on the bottom. Your intercepts, you can do your intercepts, your zeros of your numerator. These are your zeros of your numerator. This is when you set x equal to 0. So anything times 0 is going to be a 0 here. So right away you got a 0. And we can see it. We can find that on your graph as well, the 0, 0. Were you guys able to do this? So x and x minus 3. Now, don't cross out your factors yet, because the first thing you have to do is, the first thing we're going to do is factor, but don't reduce it. The second thing we do is domain. We need to find our domain. Don't worry about it unless I didn't do it. We need to find our domain. So the domain are the zeros in the denominator. So we're not allowed to use a 0 or a 3. So we're going to take that out of your number line. Remember how you take these out. Make sure you get the piece in the middle. So your domain reads -infinity to 0. Don't forget this piece, 0 to 3. And then the last piece, 3 to infinity. Okay. Now, after we get your domain, we're going to reduce. So what factor can we cancel out? What's the factor on the numerator and the denominator? X minus 3. What's left in the numerator? 1. So let's write this down here. This is our reduced rational function. So 1 over x. Now, take this one that you canceled out. I want you to circle whatever you cancel out, and right next to it, write point of discontinuity, just like that. We're going to come back to that in a minute. We're going to come back. Any factor that we cancel out from numerator to denominator becomes a point of discontinuity, and here's why. Your domain said you can't use that factor. When we graph this, it's actually going to look like it's using that number, but it's really not. So it's just a little tiny point rather than an asymptote. So just hold that guy for 1 second there. Now we continue. Let's do our vertical asymptotes. Let's do all our asymptotes. your vertical asymptote says zeros in the denominator after we factor. So from this point on, we're using this function. From this point on, we're going to graph the original one, but after we do your domain, we're using the reduced function. So we look at your zeros in your denominator after factoring. So x is equal to 0. That's a vertical asymptote. Was there a question? Everybody good? Okay, horizontal asymptote, go back to your original. Take the degree, the highest degree in the numerator, over the highest degree in the denominator. When the degree in the numerator is less than the degree in the denominator, what's your horizontal asymptote? You have one. When the degree in the numerator is less than the degree in the denominator, go look at your chart. Y equals 0. When the degree in the numerator is greater than the degree in the denominator, you don't have one. Then you have a slant. All right, so let's see what this thing is going to look like. We're going to sketch it over here. Let's get your asymptotes. Yes.
How come the other vertical asymptote wouldn't be good?
Because we had to only use the reduced one, and I'm about to show you in a second, because it's really not a vertical asymptote. It just becomes a point that we can't use versus an asymptote. So our goal is find all the numbers you can't use, that's your domain restriction, and then factor it. The factor that reduces out becomes just a point of this continuity, not an asymptote, and I'm going to show you right now when we graph it. So, a very good question. We've got your y equals, we got your x equals, we got your asymptotes here. Now, let's go to your calc. Jonathan is curious. So now we're going to graph. So put this in your graph. Be careful, if you use this way, you're going to need a parentheses around your denominator. Oops, I had to put my parentheses. All right, do a zoom 6. Let's just do a zoom 6 and see what we get. See your asymptotes? See where they're behaving? So can you spot your asymptotes right at the x equals 0? It forced the behaviors to go the opposite direction. But I really don't see where I have an asymptote at x equals 3, right? Does it look like it changed this behavior, like it caused it to split apart? It looks like it wrote right over it, doesn't it? But yet, when I go to my table, I can't use the 0, and I can't use the 3. It gives me an error on 0, and it gives me an error on 3. The 0, fine. I realize that's my asymptote. Right here, here's my x equals 0. But somewhere over here, there's a little blurb that I can't use. Your calculator it's too fine for your calculator to stop and start again. So on your calculator, it looks like it's continuous, but in fact, it's not. So if we drew your graph and we said your graph is going to look like this one, and then this one, we're going to draw a little circle right here for your point of discontinuity. That's a point that we cannot use because it's a domain restriction. The domain says don't use 3 and don't use 0. We see the asymptote at x equals 0. We see that along the y-axis. But at that little point, we got to take a little jump over that point. Now, if I look at my graph, watch. If I do a value, I say, what is there at 3? Because I'm not allowed to use it. You're right. There's nothing at 3. You can't use 3. There's nothing at 3. So what we want to do now is, what would the value of y be? if we could just fill in that little circle and continue with our graph. A point always has an x and a y, like your inflection point. You know how you find your x for your inflection point? And then we say find the y. A point has an x and a y. So now we need to find your y. So we're going to do your point of discontinuity. We're going to come back here and bring this guy back down. So x is equal to 3. Now, to find its y, you go to the parts that you reduced, and you just plug the x in. You're just going to plug your x in here. So your value of y for your point will be 3, comma, 1/3. This is your point of discontinuity. That's the point in your graph that your calculator stopped and jumped over it. And if we were to close this in, if we could remove this little point, that would be where it's at. Now, at the end of this whole year, revisit this again, but we refer to these as limits. They're calculus limits. You're actually doing calculus right now. These are calculus limits. As the value approaches something, what is happening? And this is called a removable point. Sometimes we have a jump, which is by a vertical asymptote, but a point itself can sometimes be removed. This is called a removable point. And we watch as the rest of the graph converges on that point. It comes from this end, it comes from this end, and it'll converge to that point. Now, a nice way to check you got it right is to do this. Go to your calculator, do a calc value. Now, obviously 3 doesn't work, but I'm going to do 3.0001. See how close it is to your 1/3, 0.3332? 1/3 is 0.33333 repeater rate. Look how close that is to I can't do a 3, but I can do a 0.300001. I can also do a point, and this is what we do at the end of the year when we do the calculus ones. 2.99999. See how it's 0.33334? Isn't it approaching 0.3333? Right? It's approaching that point. So that's our point of discontinuity. Okay? We have to account for that because we're not allowed to use that. Your domain said you couldn't use that. Now, let's find the rest of this. Intercepts. X-intercept. The x-intercept is the zeros of the numerator. From this point on, you're in your reduced part. You're always using your reduced one. From 3 on, we're always using the reduced one. So is there any variable in my numerator for the reduced function? Nope, I only see 1, right? No variable. So there are no x-intercepts. And let's refer to our graph. Makes sense, right? It's an asymptote. We couldn't do it. Okay? Y-intercept. Y-intercept says let x equal 0. Whoops, well, you can't divide by 0. Undefined. Therefore, there are no y-intercepts, and that certainly makes sense because my asymptote is x equals 0. Good so far? Okay. Now, here's the tricky part. Let's do your range. Okay. Is there a max and a min here? No, because it's smooth. No max and min. Let's do your range. Now, this is why we needed to find the exact point. Your y values are coming up here. It's got stuck right there. It can't go past can't hit the 0, right? So far, negative infinity to 0. Now, it jumps over. Don't forget this, it's constantly decreasing. So as we reach here, we can start right after the 0, but we got to miss that little y point right there. We can't use that value of y. It's never going to be used again because this is a function. So we skip from y to whatever this value is right here from our point of discontinuity, and then one more from 1/3 to infinity. We had to jump over that point. If you want to say 0.333, that's fine. But 1/3. We can't use that point, which means we can't use the x, nor can we use the y. So you have to jump over it. Now, if there was another piece of my graph that used it, I wouldn't have a problem. But there is no other piece of my graph that uses that. No, the range uses the y values. This is only for range, not increasing, decreasing. Yeah, the domain's up there. The domain is your x values. The range is the only time we use the y values, which is why we need that y value for your point of discontinuity. Yes?
When you found that x-intercept and the y-intercept, you use one over x.
The reduced one. The only thing we use the main one for is your domain. Then we factor, and after that, we reduce. Okay, one more increasing, decreasing here. So let's hit your increasing, decreasing. Okay, this interval over here, is this increasing or decreasing this y? Decreasing. So we're decreasing from negative infinity of the x values to when? 0. So we hit the 0, the x of 0, we got to stop. Then we resume up here, and what are we doing? Decreasing, but whoops, we have to stop right there at the 3. So then we're decreasing from 0 to 3. We're going to jump over your 3 and then continue to decrease. We have no increasing on this. That point of discontinuity is a little annoying. You have to remember that that point is there. Looking at your graph, you don't see it. But that point does not exist there. So we can't use its values at all. We can't use x of 3. It has error there. So we've got to take it out. We took it out of your domain. We're going to have to take it out of this guy too. Now, look at your increasing, look at your decreasing and your domain. Aren't they the same? Because that's all the parts we had. That has to be, it has to cover your domain. And didn't it? It did. It covered your domain because we had to take 3 out of there. Does it make sense? Kinda. Kinda, sorta. Sorta, maybe. Let me see if there's a one we can do on this one. Okay. The sheet you have for homework tonight. You're going to do the rest of this tonight. So let's take a look at number 3. Let's do number 3 together. Steps. First step. And write this down, guys. Factor. Factor, domain, and then we reduce. And then after that, we use everything that we need. But you can't eliminate your factor from your domain. So let's factor this guy. You can take out a 2. And this is a trinomial. And what does it factor to? X minus 4, x minus 5. I kind of have to squeeze that in there. Can you see that minus 4? X minus 4, x minus 5. Let's do your domain first. Your domain says you can't use the 4, you can't use the 5. Oops, x minus 5. So you're going to take the 4 and the 5 out of your domain. You've got a little section between the 4 and the 5. Can't use the 4, can't use the 5. Alright. Now we can reduce. So what factor can we take out of here? X minus 4. So we're going to circle this guy and just say point of discontinuity. This is how I want you to start. Now, write your reduced function. 2 over x minus 5. Everything from here on in uses your reduced function. From here on in. We graph the original. And I'm sorry, the horizontal asymptote also uses that. But it will work out like here anyway, so because it eliminates it. So it really doesn't matter. But we can go back to your original. So let's start with your asymptotes. Asymptotes, the vertical asymptote says go to the denominator. X is equal to 5. Because we know the other one is not an asymptote, it's just a point. Horizontal asymptote says the degree of the numerator is 1, the degree of the denominator is 2. So what's our horizontal asymptote? Y equals 0. So let's graph this guy. So we've got a y equals 0. We find that along your x-axis. And we've got an x equals 5. Okay. When we put this in your calculator and we graph it, it looks like this. It behaves nicely. There's no surprises. Except when x is 4, this is where x is 5, right? It's letting me use an x of 4 because that's where your point is. Your point of discontinuity is where 4 is. Now, for time, instead of graphing this, but you can graph this tonight. You can look at where your 4 is, and you're going to pull it out. So let's do your point of discontinuity so that everybody's with us here. Your point of discontinuity is this guy. We need to find its y. So use this reduced one. Plug in your 4. So y, if this point did exist, would be 2 over negative 1, negative 2. Your point would be 4, negative 2. So somewhere is your point here of 4, negative 2. Somewhere it has a point of discontinuity. When you graph it, it's going to look like it's continuous. Again, your calculator can't stop to go over it. You'll see 4, error. You'll see 5, error. 5 is the one we cannot remove. It's an asymptote. It's non-removable. 4 is our removable point. If we fill that in, we know what its value would be. And again, you could check it by saying when x is 3.99999, what is that value? Now, see, find the range for me and find the concavity. Hello, Mrs. Warner. Hi. Sure. Okay, fine. Melissa, if you could see Miss Crafts at the bell. Let's find your range. Your range now, look, it's moving along fine, but whoops, it's got to stop right there. At what y value? Negative 2. It can't use negative 2. It can't use this point at all. So it's coming from negative infinity. It stops at negative 2. Then it continues. Up, it gets stuck at the 0 again. Then it continues all the way up again. See your range? Let's hit your concavity. Concave up and concave down. We didn't do that before, so let's do that now. You're increasing. Are these increasing or decreasing? Decreasing. So let's hit the decreasing. It's decreasing from here to what value of x do I get stuck at? Value of x, 4. Then I'm good until, till I hit the 5. Then 5 to infinity. Oh, doesn't that look like my domain? In concavities, you got to take that out too. This is a concave up, no problem. Your concave down negative infinity to 4, and then 4 to 5. What I want you to do for homework is finish this review sheet thing. No, we're going to go over this Monday. Today's probably Tuesday. Yeah.